Hey everybody, Dr. A here, and in this video we're going to be exploring an example of frame internal loading. So let's dive into it. In the given information, we're being asked to determine the internal load functions for the frame. So here we have what's called a cantilever frame. If you notice, we have this fixed connection at A. Okay, we have this fixed connection at A. We have a member AB that's then rigidly connected to a member BC. And we see that rigid connection indicated by this boldened corner B, okay? Now, C is a free end. Then that's why we're calling it a cantilever frame, because it's fixed at one end and it's free at the other, and it's a frame, okay? On the vertical member AB, we have a uniformly distributed load of 2.5 kilonewtons per meter, and that's going to be 4 meters long. And then on the horizontal member BC, we have a point load at the end C of 20 kilonewtons, and that member is 3 meters long. Okay. Now, the first thing we want to do is notice that no location variables were defined for us. So we're going to define them ourselves. Okay. Now, you have options here. Remember, the background information video says we have a lot of options for location variables. Here's what I'm going to do. I'm going to define x1 from point C and then pointing to the right being positive. Okay, so that's going to be my x1 location variable. Now, we have this change in geometry at point B. We literally have the frame turning a corner here. So anytime you have a change of geometry, you have to define a new location variable. So at point B, I'm going to define my new location variable from point B pointing upwards, and I'm going to call that x2. Now, why am I choosing to define x1 and x2 in these particular manners? Well, if I do it this way, guess what? I can avoid solving for externals, okay? So could I solve for these externals? Sure, I could, but I can completely bypass and avoid solving for these externals if I define my origins and my location variables somewhere below this fixed connection like I did here, okay? So under solution, we'll make a note of that. Under solution, we can say to avoid solving for externals, we're going to define x1 from point C to B and x2 from point B to A, okay? Now, here's my next question. How many times do we have to make a cut in this particular problem? How many domains do we have to make a cut through? Well, the answer is going to be 2. We need to use method of sections the first time somewhere in the domain of BC, and then we use method of sections a second time somewhere in the domain of AB, okay? And in both cases, we're going to look at free body diagrams that do not include the fixed connection at A, okay? So let's go ahead and get started. I'm going to turn the page here, and I'm going to say cut 1, and I'm going to say the domain is 0, x1 up to what? What's the domain of x1? It's going to be 0 here, and it's going to extend all the way to point B, but just barely not including point B. So that's going to be 3 meters. And we're going to not have the equal sign here. So it's 0 less than or equal to x1, but strictly less than 3 meters. And, you know, if you like interval notation from mathematics, you know, you could write this as bracket 0, comma 3 meters parentheses, okay? So this is just another way of writing this same domain, all right? So let's go ahead and draw that free body diagram. So we're going to have, you know, that horizontal member, and then we have the load there. What was it? 20 kilonewtons. 20 kilonewtons. And then We have this cut right here. Now, what is this distance of this cut? Let me color code it here in red. What is this distance of this cut? Is it 3 meters? Is it 1.5 meters? No, this is literally x1, okay? You're making a cut at a distance of x1, okay? And then when we make this cut, what shows up here? Well, we're going to have a V1 here. We're going to have an N1 here, and then we're going to have an M1 here, okay? And so here we're going to be able to say sum of the forces in the x direction equals 0, so that shows that the normal force N1 is just 0. We're then going to say sum of the forces in the y direction equals 0. So here we'll say V1 minus 20 kilonewtons equals 0. So V1 is just a constant of 20 kilonewtons. And then we're going to say sum of the moments about the cut equals 0. And so we'll say negative M1. And then we're going to say minus 20 kilonewtons times x1 equals 0. So M1 is going to be equal to negative 20x1, okay? So are these functions? Well, yeah, these are functions. Now, it just so happens that N1 and V1 are constant functions, and M1 is linear. This is a linear function. You have M1 as a function of x1, and the slope of that linear function is this negative 20, okay? And of course, this function collectively is going to carry units of kilonewtons times meters, because the 20 has units of kilonewtons and x1 is a distance or a location in meters. Now, am I done? Nope, I got to make cut 2 next, okay? So I'm going to turn the page, and I'm going to say cut 2. Now, what is the domain of x2, that variable x2? Well, looking back at the original drawing, x2 goes from B all the way up to, but not including A. So that's going to be from 0, this new defined origin, up to 4 meters, but not including that 4 meters, okay? So how do I write this out? I can write this as 0 less than or equal to x2, and then strictly less than 4 meters, or if you like interval notation, you can write this as bracket 0 comma 4 meters parentheses, okay? Now, when we draw this free body diagram, what will show up? Well, we have this shape here. We've got the 20 kilonewtons, and of course we have the cut here. Now, we show the uniform load. Okay, this is the 2.5 kilonewtons per meter, and we need to show some dimension lines, all right? So this dimension line is our 3 meters. What about this dimension line here, okay? So what is the dimension line here to that cut? Is it 4 meters? Is it 2 meters? Is it 0 meters? What is it? No, it's x2, okay? And then what's going to become visible at this cut? Well, we're going to have a normal force, okay? I'm going to call this N2. And then we're going to have a shear force, which I'm going to call V2. And then I'm going to have a bending moment, M2, okay? And so then we're going to apply equilibrium here. So we can say sum of the forces, let's do y direction first. Doesn't matter which one we do first, but we'll start with the y direction. We're going to have N2 minus 20 kilonewtons equals 0. So N2 is 20 kilonewtons. And this is going to be in tension, okay? That's a normal force in tension. Makes sense. Okay, next we're going to do some of the forces in the x direction equals 0. And so here we're going to say 2.5 kilonewtons per meter times x2. And then do we have anything else in the x direction? Sure, we've got this shear force, right? So we're going to say plus V2 equals 0. We can do some rearranging, and we'll get V2 is equal to negative 2.5 x2. And again, this is a linear function now, right? It's a linear function. Collectively, this function has units of kilonewtons because the negative 2.5 is carrying units of kilonewtons per meter, and the x2 is a distance, so it's inherently got units of meters, okay? And then what about the moment function? We're going to say sum of the moments about the cut equals 0. Counterclockwise is positive. And so doing that, I'm going to say M2, and then I'm also going to say plus 2.5 kilonewtons per meter times x2 times its moment arm to the cut, which is x2 over 2, right? Because that equivalent load is right here in the middle of x2, so that moment arm is x2 over 2. And then I'm going to have minus 20 kilonewtons times 3 meters equals 0, because remember, this 20 kilonewtons is causing a rotation around that cut, and that's going to be going clockwise, so that's why that's negative here. And here I can do some rearranging, and let's see what we get. We should get, what's 2.5 divided by 2, 1.25. I'm embarrassed to say I just double-checked that in my calculator, but that's okay. Negative 1.25 x2 squared, right? Because you got x2 times x2. And then plus 60. And what are the units here? Well, this is a moment, so collectively this moment has units of kilonewton times meters, right? In fact, you can even see it here, 20 kilonewtons times 3 meters. This 60 has units of kilonewton meters, okay? This is pretty much it. So if you want to write a summary of this, what should we write? Well, we can say summary, and what we can do is we can say n as a function of x is going to equal, and then we can write these as piecewise functions, right? So on that first domain, n1 is 0, and then on the second domain, n2 is 20 kilonewtons. So we can say 0 and 20, and then we can say this is from 0 to x1 up to 3 meters, and then this is 0 x2 up to 4 meters, okay? And this collectively is going to have units of kilonewtons. We can do something similar. We can say the shear force as a function of x, and they really have two different x domains, right? That's why we're indicating with the x1 and the x2, okay? So what does the shear force have? So for V1, it was 20 kilonewtons. V2 was negative 2.5 x2. So this is going to be 20 and then negative 2.5 x2. And again, that's if you write it like a piecewise function, you can say 0 x1 up to 3 meters and then 0 x2 up to 4 meters. And this is, again, a shear force collectively with units of kilonewtons. And then finally, you can have moment functions as a piecewise function going back. M1 was negative 20 x1, okay? And then M2 was this negative 1.25 x2 squared plus 60. So writing that here, this is negative 20 x1, and then this x2 was, mx2 or M2 is negative 1.25 x2 squared plus 60, right? And we'll put the domains there, 0 x1 up to 3 meters, 0 x2 up to 4 meters, and this collectively has units of kilonewton meters. Now, here's a question for you. Okay, these are each piecewise functions. You have two domains, two pieces. One domain is defined by an x1 location variable. The other is defined by an x2 location variable. Is this the only way that we could have developed these functions? No. Remember, what the functions ultimately are expressed as is going to be based on how you define your origins and the direction that you point positive x. Okay, so if we had defined the origins and these x values differently, maybe going in a different direction, then each of these functions might be a little different. Okay, they still physically would be modeling the same behavior, but the numerical functions themselves might be a little different, because if you define an origin and an x location variable differently, then whatever functions you develop from those definitions might take different forms. But physically, they would be representing the same behavior of the internal loading of this frame. So hopefully you found this video helpful. If you did, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.